I think we are live now. Let me confirm as well. Okay, so hello everyone and welcome to my brand new channel. And this is my first ever video on YouTube and I am going live straight away without any video editing. My name is Ritu and I am a software engineer with strong interest in low-level systems, operating systems, computer architecture, programming languages, and similar low-level topics. Over the past few months, I have become increasingly interested in the ARch64, also called as the ARM64 architecture, which is used in almost all of the mobile phones that we use. Apart from ARch64, the ARM company also specifies two other architectures, which are microcontroller class processors and real-time processors. The one that I'm interested in which is AR64, also known as the A-profile processors. Um, I have spent significant amount of time reading these guides that the company has provided, and also architectural reference manuals, trying to understand how the CPU actually works. As part of that process, I have been building a bare metal kernel from scratch in C and assembly, of course. Along the way, I learned about a lot about exception levels, boot flow, exception vectors, interrupt controllers, and various other subsystems of an operating system required to bring up a system from bare metal. After going through all of that documentation and experimentation, I feel like I have a better understanding of the architecture. Looking back at my earlier code, there are quite a few things that I would design differently today. So I have decided to start over and rebuild the kernel from the beginning. My original plan was to build this kernel in Rust. However, I don't know Rust well enough yet to confidently build a kernel in Rust. Since my primary goal is to learn more about operating systems development and the AR64 architecture, I'll be implementing everything in C first. Once I have a solid foundation, I'll try to port parts of the kernel to Rust and use AI to help me learn the language and understand um, the specific patterns used in low-level systems programming. For this series, in which I'll be developing a OS or a kernel, I'll be working on a fresh Ubuntu installation on one of my spare development machines. I'll set up the entire development environment from scratch, maybe build a cross-compilation toolchain, configure qemu for emulation, and then start bringing up our kernel step by step. We'll begin with the boot process, get code executing at the appropriate exception level, establish a basic runtime environment, and then gradually add support for UART for basic I/O, exception handling, memory management, virtual memory, MMU, and there are many other things that will pick up as needed as the project evolves. The goal is not just to end up with a working kernel, but to understand um, the architecture itself and how the AR64 CPU actually runs and how to run an operating system on it. As I mentioned earlier, I have a fresh Ubuntu installation, so I need to set up everything from scratch. And when I just saw, I don't even have Git installed on it. Let me start with the directory is empty, Git is not available, so it's completely minimal installation as of now. Let me start with installing GSH and OMyGSH to customize my shell. The shell is installed. I'll install I'll install the OMyZSH now. I would like to install a few plugins and a theme that I like. It's called auto suggestion, or maybe I'll search for auto completion and syntax highlighting. So let me first install the auto completion. And this is for syntax highlighting. I also need to enter my password again, so I'll just add my SSH key into my development machine. Now let's check if I can connect it without um yeah, we are logged in. So the SSH keys have been transferred and it's working fine. Um, the shell is still not the default shell is still not ZSH. Let me once again try to install. Hmm. Still not working. I changed the shell for root. I need to change it for my user. Okay, this is working now. We are in ZSH and the syntax highlighting and auto completion are working as well. Let me quickly grab a theme that I like. I have this theme that I have stored in my .files repository. I'll just use that. Okay, this is looking much better now. And let me also install NeoVim and maybe some distribution for it. I need to install Brew before that. Homebrew. On the NeoVim website, we have an option for Brew install NeoVim, but I am not sure which uh, version it installs. Let me just run these commands. Okay, I have version 0.12 and I think it is uh, suitable for Astro and Vim. I'll install all of these requirements, even the optionals. Let me do that quick. These packages are being installed using cargo, so I think I will have to also install Rust first, and then I can install this tree to CLI. In the meanwhile, I also want to install a terminal multiplexer called Celige. I'll SCP that download into my development machine. Rust is installed. Let me fire up another shell. Cargo is working as well. Or I want to install it using a package manager. Let me try this. I'll just install the pre-built binaries now. So I'll probably move both of these binaries to slash user slash bin. And I think trace header should be in path now. Mm, yes, and also the leech as well. Okay, cool. Um, Unlock first. Trace header is installed. I'll try installing rip grep. This should be easy. Lazy git. This should be easy as well. Why is GitHub so slow? Is it down? Hmm. Let me check if I missed anything. Zelija handles clipboard, so I think I don't need to explicitly install something more. Yes. Also copied to clipboard. Yes. Um, grep should have been installed. Archie. Okay. LazyGit is installed. GDU should is installed as well. Why is the Rust taking up so much space? Okay. QTM is installed as well and looks very fancy. So I think now I can go ahead and install. Oh, I need to install Python and Node as well. Node.js. Hmm. I have Python 3.14. Okay. Do I have Node already installed? No. All the requirements and dependencies have been installed. Um, Now I can install the distribution itself. Okay, I think everything is ready now. Now I think we can get started with our building our kernel. I haven't thought about a name for this. Like, let me look for some names. Okay, let's call it um, Quark OS, because Quark, as far as I know, is a fundamental building block of matter, and it's a very small um, particle. And since I want to keep my kernel very minimal, I call it Quark. First, let's get started with our bootloader. Let's call it boot.s, and this will be our entry point to the kernel. And I'll give it a section name, uh, dot, so that I can use this in linker later to configure our memory layout. And here we can define our start label. So this will be our actual entry point of the code. And declaring this as global so that we can access this label from outside this file. And for now, let's just branch it to the same location. And let's see if this compiles. Um, I would have to write a linker file so that I configure the memory layout and which sections are stored where inside the RAM. And here our entry point will be underscore start. Then we define sections, Coming back to the linker script, mm, I'm writing this kernel for the qemu-virt-board virtual platform, the virtual board, and the execution for this RAM starts at this address. So that is the location where we need to insert our very first instruction or the entry point. Now we can define our text section aligned to 4K page size, 4K boundary, and here goes our um, the section that we defined here. So that that particular um, compiled file will be placed at the very beginning of the RAM, and after that rest all of the text section goes in here. Then we can add a section for read-only data, align it to 4296. And finally, we have our stack label, because um, eventually we will be jumping into C code, and for any function, any C functions to run, we need a stack. So we need to configure a stack before we actually transition into C code. And let's keep this maybe, let me, okay, we can have 64 kilobytes of stack. That would be 0x10,000 in hex. Now let's see if this compiles, links together and boots up. To compile this, I'll probably need a cross compiler. Uh, AR64, there's nothing installed. Let me try to find how to install this. There is no qemu as well. No. The compiler toolchain has been installed. Um, so I can now. Why can I not um, use AR64 Linux GNU assembler? Okay, I can. Let's compile it with boot. Let's compile boot.s to boot.o. Okay, and now let's link it using the Linux AR64 Linux GNU linker. No standard library. Mm, and that linker file would be linker.ld, and I have to link only boot.o as output as kernel.elf. Syntax error line number 7. Hmm. What is the error in here? Okay, this needs a semicolon. 27. This needs a semicolon as well. Hmm. We have our kernel.elf here. Now let me try to run it in GDB. Sorry, qemu, then I would try to attach GDB and check if it loops infinitely. Mhm. Machine would be the virt-board and no graphics. CPU, set the CPU to max. I think the max CPU is Cortex A72. Okay, there are newer CPUs as well. HVF, I think HVF is Mac OS Hypervisor Framework. Yes. Host, same as host for KVM and HVF. Best possible. Let me use Max and dash kernel would be kernel.elf. I cannot see anything here. Uh, that's why I would use GDB to hook into the machine and check the instructions step by step. But for that, for GDB to recognize the symbols in my code, I will need to recompile this using GDB flags. That would be dash G flag. And um, for linker I would use dash G as well. And while I am running um, the machine, I would put dash S so that it stops on the first instruction and does not move forward. One of these flags turn on a GDB server, and the other flag waits on the first instruction. And let me fire up GDB here. GDB is not installed. I'm installing a multi-arch package because I am on a x86 host and I am developing for ARch64. Now I'll try to connect this GDB to the qemu debugging server. I think it's connected. Uh, Here now I can start stepping instructions. When I do step, it just branches to the same point. That means the code has been compiled and uh, the machine is running the code as well. Maybe this could be a good starting point to make our first commit. I'll add a git ignore file. Mm-mm. Um, everything dot out, maybe everything dot o, and everything dot else. Maybe I should add a build script. uh, that runs all the commands, that all the compilation commands, so that I don't have to type it out manually. Eventually I will add a make file, but to keep our first commit minimal. I think this build script should be good enough. Everything seems to be working fine right now. I'll quickly create a repository, GitHub repository so that I can push it. I probably need to add my keys to GitHub so that I can push. Okay, so I think I can try to push now. Yes, and I can see my files here on GitHub as well. Hmm. I would now turn this into a makefile project instead of just using the um. Or first, let's try to uh, jump into the C code, create a file called um, main.c or kernel.c. Let's say kernel.c, and this would be a just kernel main with infinite loop on it. I don't have any um, CLSP language servers or something installed. Let me do that quick. The LSP is working fine, I think so, because when I save the file, I can see the file getting auto formatted. So now in boot.s, I need to set up a stack, and we already have a stack pointer in linker.ld, that is underscore stack underscore top. Um, so I move the value of the address of the stack into register x0, and then move the value of x0 to the stack pointer. We cannot directly move address of stack top into stack pointer. It has to go through a general purpose register. We cannot just simply do ldr sp pointer to stack top. This is invalid. This is not valid. Um, and then we need to branch to kernel main. Now that we have added a branch to kernel main, we need to also compile the C file that we have. So in build.sh I would add before linking. Mm, GNU GCC, and now there are a bunch of flags here. Let me first start with providing the kernel, the file names, and I will add kernel.o to the linker script as well. And now a bunch of flags. We want this to be freestanding. We do not want any dependencies on the standard library. We need GDB debugging symbols, no standard library, no start files, w, wall, w extra, and optimization. I would turn this down to 0 and add a strict alignment of the memory. So as I step through the instructions, uh, let let's first see the value of register x0 before stepping into the instruction, or let's just see if the infinite loop works and the program jumps into the C code. As I step through, yes, I can see that C code is being invoked. Now I want to check the values of registers changing the before and after executing the instructions that are setting the stack addresses. Okay, using info-reg, I can see the register values. As of now, the value of x0 is 0. Let's step instruction and now check info reg. Okay, so the stack pointer has x0 has some value, that is the address of stack top that we defined in the linker file, and this will now move to stack pointer, but we haven't executed the stack pointer instruction yet. Um, the stack pointer is still 0 as of now, and if I do another step instruction and check info reg, here now I can see that we have got the same stack pointer value as we had in x0. That means the data is being copied correctly, and we just continue with our kernel. So everything right now seems to be working fine. We have our C code working properly. Um, I think I'll commit this point. changed here. Okay, and this kernel.c is a new file. Okay, so now I think I should replace the build shell script with a proper make file. And um, I would also group these up into build directory and source directory. So we have a source and a directory for build. Um, the boot.s goes into boot.s, and the um, kernel.c would go into the source directories. and all the object files would go obviously into the build directory. I don't need build.sh anymore. Makefile and linker script at the root level seems fine. Now I want Makefile to dynamically see all the um, source files, both assembly and C files, and I should not be adding these files to Makefile to compile them manually again and again as I change or add new files. Now I want to map um, the source files in source directory to object files in the build directory. For example, um, let's say let's we give it a title object file mapping source boot.s will be mapped to build slash boot.o, and similarly source slash kernel.c would be mapped to uh, so again. Now the compiler flags. I should have taken it from the build script itself. Free static dash g no standard delivery. Okay, okay. And I would also add um, the source directory as a library so that the imports file imports work correctly. Now let's add qemu-config. Uh, I should again bring that entire thing from here as a comment, obviously. And let's bring out qemu CPU max, qemu machine virt-board. I would also um create a base flag so as to like combine the flags together. Okay, and I would create two more uh, flags to add target for running and debugging. And finally, our first target, that would be dollar target. Hmm. And this dollar target depends on all of the source files so that all of the object files, so we can use objects here because this combines both objects and object files of both C and assembly. And for every file, I would link it together. I hope this works. Now we need to compile all the C files and assembly files. And similarly, another command for assembly files. The make file is done. It was quite a lengthy one. Um, Now let me try if we can actually invoke it. Okay. Mm, where is the error exactly? Make file 55. Compile.all as files. Um, there should be a dollar all over here. Um, it compiles the kernel earlier. Um, the object files pre that we can see here are from the earlier compilation. Let me delete that. Okay, make clean removes the build directory. Make, and um, we have the make file working now. Run, looks like it is running. Make debug, and in another window I would to make gdb, which also is working fine. Let me try if I can uh, get the side-by-side view automated in tmux. Okay, this seems to be working. Okay, so now the very basic boilerplate of our project has been set up. Now let's move on to basic input output, that is UART. Um, Let me fire up a whiteboard as well. Now that we are done with environment setup and basic boilerplate. I said let's work on UART. UART is a very basic input output protocol, which is also known as serial protocol, serial communication. This stands for Universal Asynchronous Receive and Transmit. It's a very simple protocol, and we will be using PL uh, PL011 chip from ARM as our UART controller. Here, yes, we can see that the UART that the virt-board uses is PL011, and if we check Google it, it turns out it's a chip manufactured by ARM. We should be able to get an address of the UART controller somewhere here. There are only three results here, so maybe we can check in the device tree of QEMU, qemu-virt-board. Let me get QEMU base, all of this, and machine No, I think I need all of this and machine word dump dtv. Or maybe we can move this out to over at the end. This needs a dash machine flag. We have the dt device tree blob, but to read it, I think it's a binary file. Yes. To read this, I need to convert it into device tree source. I would do that using DTC. It's a device tree compiler, which is not installed. Device tree compiler. DTC is available now. So DTC dash I the device tree blob as input and output a device tree source. Now let's read this DTS file. Here we can see all the devices that are connected to the board. That is what device tree is for, and its addresses, the base addresses of the um, respective peripherals. Here I am trying to find UART or PL011 somewhere. I can see PL061, which is a GPIO controller. Here is PL011 at address, this particular address, which I can use to write data to it. So let's try it here. Um, let's just try to print one character as of now. Uh, then we can try to print strings. We can see A being printed here. That means the code is working. Let's try to print out a string. While str is available, while str is not null, just keep on printing. Star str plus plus so that the character moves forward. Okay, we can see hello world being printed here. Um, that means our UART is working, and in the end, okay, I think we should commit this code for now before I go to taking input from UART, which I think is a bit complex. I'll be back after a short break.